Household energy costs in the United States demonstrate a pattern where price increases accelerate during periods when aggregate household income contracts or stagnates. Between 2008 and 2010, median household income declined by 4.2%, while residential electricity rates increased by 6.8%. A similar dynamic occurred between 2020 and 2023, when inflation-adjusted wages dropped 3.1% and utility costs rose 14.3% nationally. This inverse relationship creates a structural mismatch. Energy consumption operates as a quasi-fixed cost. Baseline household electricity use remains relatively stable regardless of economic conditions. Refrigeration, water heating, climate control, and lighting represent non-discretionary loads. These systems cannot be switched off proportionally in response to income reduction without compromising food safety, sanitation, or habitability. Utility pricing mechanisms operate independently of consumer financial capacity. Rate structures respond to infrastructure costs, fuel prices, regulatory decisions, and utility company capital requirements. These inputs fluctuate according to commodity markets, weather patterns, and policy decisions that bear no relationship to household budget conditions in any given month or year. The result is a persistent economic friction. When incomes contract, energy costs frequently expand. When household budgets require contraction, electricity bills resist compression beyond a structural minimum. This pattern has repeated across multiple economic cycles since residential electrification became standard in the mid-20th century. I'm James Sullivan. Let's examine how households typically respond to this friction. Households typically attempt to manage this friction through consumption reduction. The most common approach involves behavioral modification, turning off unused lights, adjusting thermostats to less comfortable temperatures, limiting appliance use during peak hours, and reducing hot water consumption. These adjustments require continuous attention. Each decision point, whether to run the dishwasher, when to adjust the thermostat, how long to shower, becomes a micro-negotiation between comfort and cost. The cognitive load accumulates across dozens of daily interactions with household systems. Another standard response involves appliance replacement. Energy-efficient refrigerators, LED lighting, programmable thermostats, and high-efficiency HVAC systems promise lower operational costs. This approach requires substantial upfront capital, typically $2,000 to $8,000, depending on the scope of replacement, and delivers savings gradually over multiple years. A third pattern involves time of use optimization. Households shift electricity-intensive activities to off-peak hours when utility rates are lower. Laundry occurs late at night. Dishwashers run after midnight. Climate control systems pre-cool or preheat during lower rate periods. This approach requires schedule restructuring and sustained adherence to timing protocols that conflict with natural household rhythms. Each of these approaches addresses the symptom, the monthly bill amount, rather than the underlying structure. The relationship between household budget capacity and utility pricing mechanisms remains unchanged. The mismatch persists regardless of individual household behavior. Behavioral modification demonstrates measurable degradation over time. Studies tracking household energy consumption following conservation interventions show that initial reductions of 8 to 12% typically decay to 3 and 5% within 18 months. The sustained attention required to maintain reduced consumption competes with other household priorities and cognitive demands. Temperature adjustments produce discomfort that accumulates incrementally. A thermostat set 3 degrees higher in summer or lower in winter may seem tolerable initially, but the cumulative effect over weeks and months generates persistent low-level stress. Households frequently abandon these adjustments when seasonal extremes make the discomfort acute. Appliance replacement delivers one-time efficiency gains that cannot be repeated. Once a household has upgraded to LED lighting and energy-efficient appliances, no further reduction pathway exists within that category. The baseline consumption floor has been lowered, but the fundamental relationship to utility pricing remains reactive rather than structural. Time of use optimization requires ongoing coordination that conflicts with normal household patterns. Evening hours are when families are home and most active. Restricting appliance use to off-peak hours means either staying awake late to manage laundry cycles or waking early to adjust climate systems. The routine friction of this approach makes sustained adherence unlikely across years. All three approaches share a common limitation. They assume the household must continuously adapt to external pricing dynamics. The locus of control remains with utility rate structures, fuel markets, and infrastructure costs. Household behavior adjusts in response to these external forces rather than operating independently of them. A separate category of response formats exists outside the behavioral modification framework. These formats involve establishing household-level generation capacity rather than optimizing consumption of grid-delivered electricity. This category includes multiple technical configurations: small-scale wind installations, micro-hydroelectric systems where geography permits, solar panel arrays with battery storage, and various forms of mechanical or electromagnetic generation occupy this space. The common characteristic is that electricity production occurs at the point of consumption rather than through a centralized utility relationship. These formats operate on a different economic structure. Instead of monthly variable costs determined by external pricing, the household incurs a front-loaded capital expense followed by maintenance costs that are generally lower and more predictable than ongoing utility payments. The relationship to utility rate fluctuations changes from direct dependence to partial or complete independence. The format category exists across a spectrum of scale and complexity. Some configurations maintain grid connection for supplemental power or emergency backup. Others operate entirely independently. Some require significant installation complexity and ongoing technical maintenance. Others involve simpler mechanical systems with minimal intervention requirements. The category has expanded considerably in the past 2 decades as component costs have decreased and technical documentation has become more accessible. What previously required specialized electrical knowledge can now be implemented using widely available materials and standardized procedures in certain format types. One format within this category involves compact electromagnetic induction devices that amplify existing electrical current from small source inputs. These devices typically consist of wound coil assemblies in specific geometric configurations, housed in portable enclosures small enough to be positioned in a basement, garage, or outdoor utility area. The typical implementation involves connecting the device to a low-voltage source, a small solar panel, battery bank, or even parasitic draw from existing household circuits, and routing the amplified output to selected household circuits or a supplemental distribution panel. The physical footprint is comparable to a medium-sized portable generator, but operates silently and requires no fuel. These devices generally involve a single installation procedure followed by minimal ongoing interaction. The coil assemblies contain no moving parts beyond electromagnetic fields, which eliminates mechanical wear patterns common to motor-driven generators. Maintenance typically consists of periodic wire connection inspection rather than continuous operational oversight. The format fits within existing household infrastructure without requiring structural modifications. Most implementations connect to standard electrical panels using conventional wiring methods. The devices operate continuously in the background of household routines rather than requiring activation or management for each use. This format represents one approach within a broader category of household-level generation systems. It is not appropriate for all contexts. Geographic factors, local electrical codes, existing infrastructure configuration, and household technical capacity all influence implementation viability. The underlying economic pattern, the inverse relationship between household income conditions and energy cost trajectories, persists independently of any individual household's response strategy. This structural dynamic operates at the level of utility pricing mechanisms and regulatory frameworks that determine how electricity costs are calculated and distributed across consumer populations. Alternative formats exist. Their presence in the market reflects sustained demand for options that restructure the household-utility relationship rather than optimize behavior within existing dependencies. Whether any particular format addresses the friction effectively for a specific household depends on variables beyond the scope of this analysis. The mismatch between budget flexibility and energy cost volatility continues as a recurring feature of household economics in systems where electricity pricing operates independently of consumer financial capacity.